Alright, so we are using the conservation of energy to problem solve in this problem. And first, we'll just read it out. A spring with a spring constant of 200 newtons per meter is originally 30 centimeters in length. A physics student then pushes a 3 kilogram block onto a spring so that the spring is now 10 centimeters in length. The block is initially at rest on the spring in the position shown, and that's this picture here. Assume that y equals 0 at the bottom of the incline, so I'll add that in right there. How much is the spring compressed in meters? So this problem isn't asking for anything particular about energy. It's just asking us a fact about this spring. And everything I read in the problem about the spring told me that it was originally 30 centimeters. And then, when the block was pushed in on it, it got squished together and now is only 10 centimeters. Well, that means it must have been compressed 20 centimeters. It just started at 30 and got pushed in. That's something I can just think about with words. And if I want to convert that to meters, that's 0.20 meters, 20% of a meter stick. Watch that you can talk about what compression means. How big was something in the beginning? How big is it at the end? B starts to talk about energy. How much total energy is stored in the block Earth surface system when it is in the position shown above? So the block Earth and surface are places where these energies could be. And I want to figure out what types of energies I could have. I could have spring potential energy, gravitational potential energy, and kinetic energy. I have spring potential energy when a spring is compressed or stretched. I have gravitational potential energy when there's a mass in a gravitational field at a height. And I have kinetic energy when a mass is moving. So here, I don't have any gravitational potential energy in this position because we're at the bottom where y equals 0. So there's no height. And I don't have any kinetic energy because we're told the block is initially at rest. So there's no speed. So the total energy right here just happens to be, and the energy total in the beginning equals all the potential and all the kinetic in the beginning. But it's just spring potential energy in the beginning. That's all there is. So I'll say 1/2 k delta x squared. Now, when I underline these known values, if you don't know what they are, you have to sit down and make sure you can write what each of every single one of these variables is. You can't use your tools in woodshop if you don't know what they mean. You don't know what they are. I can't use a hammer unless I know what the hammer is. And I need to use K, the spring constant, and I need to know that from the problem, that's 200 newtons per meter, how stiff the spring is. Delta X, how much it's stretched or compressed, is 0.2 squared. And it turns out what we get for the total energy in this system is 4 joules when we calculate that out. The block is then released from the spring, and the spring returns to its original length. That tells me that there's no more spring potential energy in this system. The block slides along a very smooth surface. There's no outside friction converting any of this energy to heat energy, and reaches the point shown above 10 centimeters above its original height. And the original place where it was y equals 0. So now this has some height. That gives me interesting information for later in the problem. How much total energy is stored in the block Earth surface system when it's in the position shown? Well, that I can do by thinking about the deal with energy. And the big deal with energy is that in a closed system, you are never going to have energy leave the system or come in. All I have is whatever energy I have in the beginning, I have at the end. And if there were 4 joules in the system here, there's 4 joules here, and here, and here, and 4 joules here, and 4 joules here. So that means right here, there are 4 joules of energy in our system because the total energy has to be conserved. The speed of the block I can find by using those 4 joules and realizing those 4 joules equal all the potential energy in the system at the end and all the kinetic energy in the system at the end. The types of potential energy, well, it has height and the spring isn't stretched. So all we have is gravitational potential energy. And it is moving. We're asked to find the speed of the block. So I have kinetic energy final, and that's 4 joules. Setting that up as 4 joules equals mgy plus 1/2 mv final squared. and I say V final and Y final because there are final heights and our final kinetic energy. This is the end of the problem. I'll then say, okay, well, let me just plug in what I know. I know M is 3 kilograms. I know G is 9.8 newtons per kilogram. And I know Y is 0.10 meters. That's that 10 centimeters converted to meters. 1/2, 3 kilograms times V final squared. And I have that this is equal to 4. I have all my known information except for one thing. And I can solve that V final is 0.84 meters per second. Be able to do a problem like this for next class. And make sure you can know what every single one of these terms means, how to use them, and the big idea that energy is conserved in a closed system.